video. My YouTube video. Ah, it is Nate. Hey! Hey, Nate.
Hi.
All right. Oh, my sound's not on, bud. Here, say something. My sound's on now.
Hello.
All right. So let's back it up to improper integrals. So distracting. All right. So again, improper integrals. The first three questions we're going to do, either one or both of the bounds are infinity. This is a lot easier to see and a lot easier to know you have to deal with. What we're going to do when we get back from that break is we're going to deal with ones where there is a vertical asymptote at or between the bounds. If you notice, these kind of just look like normal integrals, but think of like for this one, if I plug in 0 in the denominator, I got some risky business going on. So I got to make sure that I'm paying attention now anytime I see an integral with bounds. So let's start with these first ones. And I'm going to see if you can answer my vague line of questioning with the specific answer that I would want. So the reason we're going to have to use a lot of notation in these questions is because we're not allowed to really just use infinity like a number. So I'm not just allowed to plug in infinity as a bound like I normally would after I integrate, because it's not really a number. Can you think of anything that we have done this year in calculus where it's something where we want to plug something in, we're not allowed to, so we're going to see what happens when we get like really, really close, when we're starting to approach that thing? Yeah, we're going to talk about limits here. So essentially, we're going to limit out the bound with another letter, and then we're going to integrate like normal, and at the end, we'll have the extra step of evaluating a limit. So it's kind of comboing a lot of notation and a lot of stuff that we know already to get around plugging in that infinity as a bound. So let's start. So if you see infinity in your bound, the first thing you're going to want to do is replace that with a limit at the front and a letter. Now, I tend to use the same letters all the time. It's the letters most textbooks use. I'm going to always use A for my bottom bound and B for my top bound. You don't have to do that. You can use whatever letter you want as long as it's not in the integral or a letter that already stands for something like E. So I'm going to do as B approaches infinity, from 1 to B, and I'm going to choose to rewrite the integrand here just for the sake of my eyeballs, because I don't like the dx on the top. But would you agree that's 1 over x dx? Cool. All right, now that I've limited out this bound, really this limit's just going to stick around until my very last step. I'm just focused on evaluating this guy right here. That limit is just going to hang out at the front until the very, very last step when I evaluate it. So, limit stays. What is the integral of 1 over x dx? Natural log, absolute value of x, and we have from 1 to b. All right. What do you think I'm going to do next? Yeah, let's plug in our bounds like we normally would. We're still doing this integral. Since b is a variable, I'm going to keep the absolute value bars on it. I know we're taking that b towards infinity, but I'm going to assume that b is just a random variable that I don't know yet. And then minus natural log of 1, dropping those absolute value bars because I do know 1 is positive. Speaking of natural log of 1, anyone know what that is? That's 0. A lot of, I'm going to try to make a note of some of the values we should know today. There's going to be a few. That's one of them. So now that we've kind of evaluated our whole integral, we're going to start evaluating some of these numbers. So let's talk about another value we should know, and that's the value that natural log of x approaches as that x or that b, so the innards of your natural log go towards infinity. Anyone know what the graph of natural log of x looks like? Nice. My second block was just as silent. Does anyone know what the graph of e to the x looks like? The exponential. Remember that it gets like super big, super fast, this guy? Okay. Yeah, so this is e to the x. Now, why would I bring that up? E to the x and natural log are inverses of each other. So their graphs reflect along the line y equals x. So this is what natural log looks like. Yeah, kind of like the opposite, a reflection, if you will. Yeah, so like if I did natural log of e to the x, I would get just x. If I did e to the natural log of x, those are those inverses. So my question now, we're trying to evaluate this first part of the limit, right? So I'm trying to say the limit as b approaches infinity of natural log absolute value of b. So I really want to know this natural log guy right here. Where is that green arrow going? What y value is that approaching? Yeah, this is a very slow growing function, natural log of x is, but it does grow forever. So we will get infinity out of that limit. Now, I want you to not write what I'm writing right now, but I want to show you something that we're trying to avoid. What I'm trying to avoid by doing this limit is writing this down. At no point do I want to see that in your work. The entire reason we're doing the limit is avoiding writing that down. So what we want to do is we want to go straight to the value of this limit, which is infinity. And I could do -0, but that's not going to change anything. So this is a little bit interesting. We're getting our first integral that doesn't equal a number. That has not happened before. So let's give some context to this and some verbiage for what this means. What did an integral mean on a graph? The area between our curve and our x-axis, right? Let me pull up some Desmos so I can show you. Hi again, Nate. Yeah.
If one of the bounds is infinity, then how would the answer not be infinity every time?
If your function kind of gets, so let me show you what this one looks like. It'll make more sense. Maybe not. It might not make more sense, but I'll try. What was our 1 over x less than equal? Hold on. How do I do this? Y less than equal. There we go. What was our top bound? 1? All right. So this is the thing that we're looking at here. So we're saying that the area of this red thing, even though it gets super skinny and goes infinitely on forever, this guy would actually have infinite area. To answer Nina's question, it's a little bit of a wishy-washy answer, but sometimes that function will get close enough to that axis, like fast enough, where it will be a finite answer. And there's kind of a boundary line for it. It actually is the function 1 over x is kind of that boundary line for it. But sometimes, even though it's infinitely long, it is bounded by a number as the area. So let's figure out a word to call this. We're going to use a set of words, and we're actually going to use them again when we talk about series. If we get something that is infinity or something where we can't evaluate this limit, most of the time it's just going to be positive or negative infinity, we are going to say this integral diverges. All that means is I can't get a finite number out of my integral. So that means our integral diverges, like the cool movie Divergent. We're actually going to talk about series later on, so like adding up infinitely many numbers, and one of our entire chapters is about whether things diverge or not. I was going to theme it on all of the divergent stuff, and then it just became overwhelming because there's too many. Anyone know the opposite of the word diverge randomly? Converge. So we are going to have divergent integrals. That's essentially I either can't evaluate the limit at the end or I get some form of infinity. Converge is just going to mean I get a number. So literally every integral you've done up to this one today has converged because you've gotten a number as your answer. So don't think too hard about those words. It just means, do I get a number? Do I not get a number? So I may say in my directions, I think I do on both the problem set, well, not the problem set because I didn't give directions for that specific section, but I was looking at the test to kind of edit it. And in the directions for all of the ones with bounds, it's going to say indicate whether the integral converges or diverges. So you'll give your infinity if you can, or just the limit doesn't exist, whatever, and you'll be like, this integral diverges. If you get a number, you're going to say this integral converges. All right, let's do a very similar question, just with a different type of infinity in your bound. Can everyone see why this is an improper integral? Yeah, the infinity, specifically this negative infinity in the bottom. So again, I think these ones are a little bit easier because they're a little bit more in your face. It's like, hey, I am infinity. All right, I'm going to personally choose to limit out the bottom bound with the letter A, just because I do A for the bottom and B for the top bound. If you want to use the same letter as the first letter in your name, go for it. As long as your name is not Xavier or Emery. Sorry. E means something already. Or does anyone else have a bad letter? Amelia. Nope. No good. Elena. No good. Oh, a lot of E's in this room. All right. All right. So I'm going to do A on the bottom, 0 on the top, E to the, whoa. E to, mm-hmm. So it really doesn't, and I think that's a good notice there. It really doesn't change what we're doing with the problem. Really, we're kind of sandwiching our question with a first step, a last step, and just some notation on the side. Pretty much the entirety of the problem is exactly the same. We're just trying to avoid using that infinity like a number. All right. Thoughts on this integral? This integral involves something we've been talking quite a bit about, especially while we're working on our problem set. Anyone want to make some comments about the e to the 2x as we integrate it? Oh, I heard a whisper of it. Someone in the back whisper louder. Yeah, there's some u sub. Now, does anyone know what number is going to pop up in front of this guy? 1/2. Now, if you don't know why, we would do du is 2 dx. There is no 2 there, so we have to move that over as a 1/2. Again, your life is going to be a lot easier, especially on your problem set, if you can start doing that one in your head. Some of the verbiage that's helped some people, it's a lot like a reverse chain rule. As long as that derivative, that du, is just a number, we can really think of it as like the reverse of a chain rule. So I'm going to keep my limit out front. I have not evaluated it yet. And I'm going to do, 1/2 e to the 2x, and my bounds are going to stay. Yeah. So if there's anything up in that exponent other than just x, it's kind of like our inside function. That exponent is our inside function. Yeah. So I'm kind of, especially for this stuff, since that a is in there, the bounds are a little bit weird. I would like to avoid changing my bounds by actually doing the u substitution. So that's why I'm kind of doing it in my head, because otherwise I'd have to change the bounds to 2a on the bottom and, 2 times 0 is 0 on the top, just to avoid all of that messiness with the substitution, especially if that had been even weirder. If I can just do this, I think it's a lot easier of a process. Yeah, if you want to skip substituting out, if you can see it, there's a lot of integrals where you probably will be able to see the u substitution. So like for me, if I see like this, I immediately go, oh, 1/2 natural log x squared plus 1. Because this is the u. Yeah, so that takes some time. You might not be comfortable with that yet. You might be comfortable here. That's totally fine. A lot of us are getting comfortable with like sine 2x. Cool. I know this is going to chuck a 1/2 out in front. Because I'm keeping x in my integral, so we changed the bounds so that we would keep the integral in terms of u. So I don't have to change the bounds because I'm going back to x's. All right. All right, let's plug in our bounds. I've got limit as a approaches negative infinity. As I plug in 0, I'm going to get e to the 0, which is 1. So I'm going to go 1/2 for the first term, and then 1/2 e to the 2x, or nope, 2a, excuse me, in the second term. Now, a lot of these limits at the end, because now that I've done my whole integral, so like Nina was saying, this is kind of our normal process here. Now we're on to the new stuff of evaluating this final integral. A lot of this is sometimes going to be something you're going to want to do scratch work on. So just like we were kind of investigating our graph before, this piece is something I would do scratch work off to the side. Again, I really want to avoid, in the context of my problem, plugging in negative infinity, but I'm going to kind of do that in some scratch work off to the side that's not equal to this problem. So I'm going to look at, I'm going to forget the 1/2 for a second. I'm going to look at the e to the 2a, and I'm going to see what happens if I plug in negative infinity to that. Notice that this work is off to the side. It's not part of my problem. This is just me investigating in some not notation worthy work. What? You can. 2 times negative infinity, still pretty big, still pretty negative. But what do negative exponents do? They go to a denominator. So I'm going to do 1 over e to the infinity. E to the infinity is pretty darn big, right? So we're talking 1 over infinity, which Rashad has thrown out into the world, is going to approach 0. Do you guys agree with him on that? We take a number like 1, divide it by something so huge it's infinity, we're going towards infinity. So the work I actually want to be equivalent to what I'm doing is 1/2 minus 1/2 times that 0. Notice in the actual work that's like the work to be graded, I'm going straight from there to the 0. Yeah. You can think of a couple of things. E to any power, that's getting really big. So think of multiplying together infinitely many e's. That's going to be really big. Or the graph of e to the x, it's going to infinity.
Okay, got it. You divide it by a bunch of these.
Yeah.
Okay, right. Got it.
So if it was like not a negative in the first place, and it was just like e to the infinity, how would you do that?
That's going to get really big, right? We did it right here. All right. As I'm doing this, I get 1/2 minus 0, which is 1/2. So my answer now is actually a number. So does this integral converge or diverge? Converge. We're not thinking too hard about that. Whoa. Spelling converge is. Again, most of the time you're either going to be asked, like, does the integral converge or diverge, or you're going to be asked for the value of the integral. A lot of the times for multiple choice, you'll see like evaluate this integral. Maybe like here, the answers might be like 0, 1, 1/2. And like answer choice D might be like, oh, the integral diverges. Yeah.
Can you show what this looks like on decimal?
Yeah. I know. E to the 2x. And then what were my bounds? Negative infinity up to 0. So x is less than 0. So notice here, compared to the last one, would you agree that this one is approaching that x-axis a lot faster? Yeah. So that's it's a wishy-washy explanation, because how do I decide what's faster or what's not?
Where it actually hits
It won't.
Oh, I thought.
Because it's e to the 2x as I'm taking towards negative infinity. So if I manage to reach infinity, it would hit, but that's not a place we can actually like go to.
1/2 then? Like how does the answer like 1/2 if it's?
It's infinitely long, but the area is finite. There's actually a really cool example. Oh, here, I'll make it make less sense. All right, so this is a definite tangent, but this is a really cool example. We'll be able to talk about this at the end of unit.
What is it?
It's a paradoxical thing. So this is a cone that's infinitely long. If you tried to fill it with paint, so the volume of it is actually finite. So I could fill it with a finite amount of paint. But if I went with like a roller and tried to paint the whole thing, its surface area is infinite.
I literally don't get it.
Moral of the story, infinity makes things weird, and it doesn't make it hurts our brain a little bit to think about them because we can't actually reach infinity. So your brain's having a hard time processing.
What is the answer of 1/2 then?
So that means this infinitely long area has area 1/2.
Of 1/2.
Yes. So like if this could be painted with gallons of paint, I could buy half a gallon of paint and paint this infinitely long thing.
Okay.
It would take me an infinite amount of time, but I could do
That's
it.
all you need.
That's
Yeah.
what you put
That
inside.
doesn't make it Would you need an infinite amount?
No,
But
it's
don't
small
want
enough.
infinity, so how can you-
It would take you an infinite amount of time, but it would take you a finite amount of paint. Yeah.
Is that like a thing where like you take like and like and do a circle and then you can draw
A Mobius strip?
both sides without
No, that's another cool math thing though. Yes, a Mobius strip has one side. We can investigate all of these things. Not right now though. All right, let's do one more thing and then we're going to take a solid break here. This is going to be your kind of most annoying case. And that is because, what do you notice? We'd have two infinities. Now, one thing we're not really allowed to do because we are in single variable calculus and not multivariable calculus, though I don't think they do this in multi either. We're not going to slap two limits on the front of this thing. We're only allowed to limit out one bound at a time. So what we're going to have to do is we're going to have to break this integral in two pieces so that we have negative infinity on the bottom bound of the first one and positive infinity on the top bound of the second one. Is that annoying? Yes. So you probably won't see these very often. This one also has some cool values that we're going to talk about. So I'm going to start with negative infinity here. And I'm going to add on wherever we stopped up to infinity. Now I'm leaving that blank for a purpose because I want to talk about our options. So the problem here is we need to choose a place. We need to choose a place, but the cool part is we can choose any the heck place we want because we have the entirety from negative infinity all the way up to infinity. We just have to break this somewhere, and it doesn't matter where. But for notation's sake, we do have to break it. Would anyone like to volunteer a value? 0. That's where I would do too. It doesn't matter, but usually when I'm plugging numbers into things, 0 is the easiest number to plug in. That being said, this time it's a choice. So when we get to the second page of the notes and have to break it, that won't be a choice. Here, this is a choice. You could do 1, you could do 5, you could do 3,731. That's fine. Those are all between negative infinity and infinity. All right. As I limit this out, I'm going to start pondering, and hopefully you will too, how to integrate this function. I told you that the integral of this guy would come back because he does cool things as we go to infinity. This is the moment I was talking about. Any ideas? 1 over 1 plus x squared. Oh my goodness, someone remember. It's arctangent. We don't have to worry about u and a because u is x and a is 1. So this is just going to be arctangent. Are you guys cool if I do arctangent and plug in my bounds at the same step? So do like, go from this step to do like arctangent of 0 minus arctangent of a? No?
split it up?
Yeah, that's fine. Maybe some of you should start the problem set a little bit earlier. That was not directed at all of you. That was directed mostly at like all my classes. You'll work on it Thursday night. All right, good luck. I don't check my email that much. Yeah, you could be like some of my second block kids and just show up in the morning without asking. Austin. Oh no, I had two people show up at like 8:15, and I was like, whoa, whoa,
That's early.
whoa. And I was like trying to get stuff done. It's fine. They called the main office. The main office called me down. They were like, Miss Hefty, you got students in the main office. I was like, I didn't invite anyone. It's okay. That's fine. I do like people coming in the morning, even if it's unannounced. All right. So arctangent. It has been a heck of a long time since we talked about arctangent at all. Specifically plugging in places to go. So arctangent is really, really cool, and there are kind of 4 values that we need to be able to evaluate on arctangent. So let's do some graphing to investigate. I think I can type arctangent here. All right. So here's arctangent. I'm gonna get the grid off. At least, yeah, let's just get rid of the whole grid. All right, anyone have some ideas of where it looks like there's 2 pretty strong horizontal asymptotes, right? So when I said this function does cool things as I go towards infinity, that's what I meant. As I go towards positive infinity, this does approach a number, and as I go to negative infinity, it also approaches a number. They're 2 different numbers, which is wildly cool. And we're going to investigate both of them. Now, to give you some context, remember arctangent and tangent are inverse functions. So I'm really looking at where these vertical asymptotes are on tangent to find where the arctangent goes towards positive, negative infinity. So does anyone remember where these places were, where our regular tangent had its vertical asymptotes? Ooh, negative pi over 2. So here we go. Let's talk y equals negative pi over 2. Nate said something?
I thought I heard it too.
Wait, I thought you had to make the integral negative because you flipped the bonds. Wait, yeah, I'm not monitoring the chat. So if you want to talk to us, make sure you say it out loud. My sound's on, yeah. Anyone think they know the other one? This graph's pretty symmetrical.
Pi over 2.
Perfect. All right, so those are the 2 values that we need to know as I go towards positive infinity, positive pi over 2, negative infinity, negative pi over 2. Another thing we need to know is 0, comma, what point is on this graph? All right, now, better one, 1, comma, what point is on this graph? At what angle is tangent 1? Hint, it has a pi in it.
Pi over 3.
No. 4. All right. So arctangent, negative infinity, arctangent, positive infinity, arctangent 0, arctangent 1. Those are the 4 values you need to know for arctangent. I will not ask you to evaluate other ones most likely. So let's give ourselves a little bit of a graphy poo.
I think it's just supposed to be like a fun. This is the graph of. Are we gonna have to remember all of these graphs? Or like on the cell?
You'll need to know those 4 values, so I'll write them down.
Oh no, it's 6.
So as we go towards positive infinity, arctangent goes towards pi over 2. As we go towards negative infinity, arctangent goes towards negative pi over 2. Arctangent of 0 is 0, and arctangent of 1 is pi over 4. Now, this one won't come up as often as, say, like natural log. So, like natural log of 1, natural log of e should be a little bit bolder in your brain than these guys. But if you're really rolling for that 5 on the AP test, which most of you should be, these are some values that will become helpful. So, let's evaluate arctangent of 0. What did we say that was?
0.
What did we say arctangent of A was if A is going towards negative infinity. All right. Now I'm adding the second set of values on. Where are we going as arctangent of B as B goes to positive infinity? Pi over 2. And then arctangent of 0 is still 0. Now notice this first 0 and this last 0, we added and subtracted the same value. That's why that top bound, bottom bound situation, that's why I could have chosen anything I wanted. So it doesn't really matter. We've got a positive pi over 2, a positive pi over 2. So this whole thing is equivalent to pi. Last question before we take a solid break. Converge or diverge? Converge. Remind me again, why am I saying converge? I got a number. All right, so when we get back from break, I will say the integrals when we get back from break are a little bit easier, but the harder part is going to be to decide why we need an improper integral. So let's take, oh wow, my clock is big. We don't need an hour and 15 minutes. Let's go with 4. Yeah, if you're leaving, just kind of catch my eye and let me know that you're going. Okay, bye, bye, bye. Okay, bye. We're not going to do a nose check today because I didn't like the nose check that I made.
Okay.
Yeah, that's it.
Thank you.
Thank you. Wait, Nate, did you want me to try to answer your question? Are you there? If you did.
Yes, please.
What? So wait, what is it? Where? Can you give me a reference as to where you asked that question?
The one that's 0 and negative infinity, because you did A is
Okay.
approaching infinity. Don't you have to make that negative?
So I don't think I ever flipped the bounds anywhere. So where are you talking?
I don't know.
Okay, so I had the lower bound was our negative infinity, so I kept the A at the bottom. I don't think I ever flipped the bound.
Gotcha.
When I used the negative infinity, that's kind of the green work off to the side that pushed that infinity down to the denominator. So that was kind of where the negative went, if that's the negative you're talking about.
Okay.
Okay, if I'm not answering your question and you can rephrase, just let me know.
Okay, we'll do.
All right, I need a beverage.
Let's you put the time for 4
4. Only if you can take the whole AB test and get 100.
That's probably not
You want to take the Algebra 1 test instead? Inequalities.
I'm gonna do all right.
Do you remember when to flip the inequality sign? When you divide or multiply by a negative number. That is correct. That's the thrilling test they get to take tomorrow.
I don't think I could do a geometry test.
Oh, I could not do geometry test. I know some of the geometry teachers are always like, oh, calculus must be so hard to teach. I'm like, I don't know how to do geometry. Like, it's all what you use. I think architecture uses a ton of geometry. My spatial reasoning isn't the best. That's why Calc 3 was hard for me. Multivariable calc, it's just, there's a lot of spatial reasoning that you need once you get into double and triple integrals. So it's difficult.
He didn't care. He doesn't care. I'm never helping the kid. Okay. Well, yeah, so many teachers. That's great. Yeah. Let's go again. Let's go.
All right, we ready to roll? We have been rolling, but I would like to roll some more. All right, so we are going to start our second set of questions. These questions are definitely a bit different and a bit sneakier, if you will. So these are going to change the way we look at a question with bounds, because this looks like a normal integral, right? It looks like, oh, I just integrated, I just plug in my bounds. Sometimes that'll work, and sometimes that'll make me very, very wrong. So let's look at the graph of this to investigate why it's a little bit different at first. All right, hold on. What are we looking at? We're looking at 1 over the cube root of x, CBRT, and SQRT. I know. Desmos is really just winning the game here. Cube root. You can also just type in INT and you get an integral. All right, and we're looking from 0 to 1. All right, so you can kind of already see that the thing that I'm integrating doesn't look quite normal. So it's kind of the same idea, just rotated about 90 degrees or one way or the other, depending on what you think of those questions that we did before. But we've kind of got this infinitely long area, just now it's going up. So 0 is this problematic bound. The part that makes these questions a little bit harder is I have to check for that. So it's not going to come out and say like, hey, improper integral here, like do your limit thing. You're going to have to now look at every set of integrals with bounds with a little bit of skepticism. You're going to be like, you cool or you not cool? This guy, not cool. So I could have this situation where that's happening at one of the endpoints, but it could also happen between. We're going to start with two that happen at the endpoints. The one that's between is a little bit harder. There is one slight other caveat, and that is because we're only going to be approaching 0 from one side. So do you guys remember one-sided limits from the very beginning of the year, the little plus or the little minus? We're going to be using that. It won't make a huge difference all of the time, but it will make a difference some of the time. So we're going to do it every time. So let's start with our notation. I may pop back and forth between the graph to help us out with some of these decisions. So I'm going to limit out the bottom bound. That's the one that's making my denominator 0. Now there's a bunch of ways to make a function not continuous. The one you're going to see like 99% of the time is what makes the denominator 0. In fact, I can't really think of another way to do this question and make it improper other than that, but I don't want to say always because I get in trouble when I say always. All right, A to 1. Let's write this like this. All right, now I do have to say 0 plus or 0 minus. There's a couple of ways to think about this. I have a little bit of a shorthand, and since we were talking about shorthand for trig earlier today, I'll show you. But looking at the area, am I concerned with numbers that are slightly bigger, so slightly to the right of 0, or numbers that are slightly smaller, slightly less than 0? To the right. So I'm coming in from the right-hand side. So I want, that's my calendar, I want to put a little plus right here. Sometimes you may see me do a little number line to kind of indicate this to myself, and I draw a little arrow. So if you see that, that's just me checking which side it's coming from, just to like really be like, brain, do you know? If that's the one you're limiting out. So if I were limiting out, let's say I saw like an x minus 5 on the bottom, and my integral went from 5 to 7, you might see me do 5 to 7. I want this stuff. I'm going this way. So you really just want to know what side you're coming in from. Now, it won't make a difference a ton of the time, but every now and then it'll determine what we're doing. All right. So again, our focus, kind of like Nina said, this doesn't change a whole lot of what we're doing. Our focus is just on integrating this at this point. We did our first step, our first piece of sandwich bread. Here's the big part, whatever you put in your sandwich. That's like my dad's favorite question to ask in large groups of people to learn about people. No, what's your favorite? What's the best sandwich? And then he likes to be aggressive and be like, I know the right answer, but I won't tell you until everyone's.
What is the right answer?
I'll reveal it at the end of this question.
Okay.
All right. Next number talk. What's the best sandwich? All right. How am I going to integrate this, y'all? I'm so stuck. Do I need you, son?
No, bring it to the top.
Bring it to the top. What power is it going to have then? -1/3. Nice. Now, remember, sometimes integrals are actually just easy, and you can just do them with power rule. This is one of them. So not all the time. I know we've gotten very fun and fancy with our integrals. Sometimes they're just easy to do. So since I just have x to some power, I'm going to add 1 to my power. What fraction will be my power? 2/3. What number will go out front? 3/2. Let's multiply by our reciprocal. Here I'm going from a to 1, and I'm still just going to plug in these bounds. So the interior process of this, very familiar, not exciting. Maybe exciting to you. I don't know. I'm not excited currently. 1 to the 2/3 is just 1. So my first term is just going to be 3/2. And then I'm going to do minus, that's supposed to be a 3, over to a to the 2/3. Now, unlike the infinite limits, these ones sometimes will kind of work out super nicely. What I mean by that is 0 going to cause any issues at all if I plug it into a to the 2/3? Do you know what 0 to the 2/3 is? Yeah, it's just 0. So with these number ones, sometimes it's going to be super, super easy to plug in. Direct substitution will work. This is one of those cases. So I'm getting 3/2 minus 3/2 times 0 to the 2/3. I get 3/2. Do I always split the fraction? Are you talking here to here? Yeah, because when I add this, so it's me dividing by 2/3. I always just find it easier to multiply by the reciprocal of that. Victoria, what's up? So are you saying, could I have just done like this piece? So in this question, yes, it would have worked just the normal way. You will run into problems, and we'll run into one later today, where the answer to that would be no. So the weird thing about these is sometimes they work just the way we want them to, and sometimes they're a little creepier. So let's try one that's creepier. Do you want to say whether it converges or diverges? Yeah, it converges. You can write that down if you want. What? If the directions say indicate whether the integral converges or diverges, we just had an integral, so I was just gonna leave it.
What's the best answer?
What?
What's the best answer?
Oh, that's right. What do you guys think the best answer is? My dad's answer, which is a little pretentious, is the day after Thanksgiving turkey sandwich with like stuffing and cranberry sauce.
Wrong.
I don't know. My dad makes a really good stuffing, so it is a really good sandwich. It's probably my number 2 sandwich. My top sandwich is the bacon, egg, and cheese on ciabatta from South Street. So specifically from South Street. South Street's the best. I go there like probably twice a week. All right, is this an improper integral? Someone said yes. Yeah. How do we know? All right, looking at this, if I plug 0 into the bottom, am I going to get 0 in my denominator? Yes, so that's what I'm looking for. Where is the denominator going to be 0? If that's at or between one of my bounds, let's limit it out. I'm going to go A again, just because it's my bottom bound. That's kind of my strat there. Does anyone know whether it's going to be 0 plus or 0 minus? 0 plus. We're coming at 0 from numbers that are bigger than 0, like 1 and 2. So I'm going to go 0 plus. A now at the bottom, 2 at the top. I would write 1 over x cubed, but can we do that negative exponent thing again? Can we do negative 3? No? Yes? We good? Yeah, cat. Yeah, yeah. Unless your bounds are randomly backwards. So, because I could theoretically make the integral like 2 to 0. You probably won't see that, so you will want to investigate, but most of the time. Yeah. The top bound's negative. Yeah, so like if I made this negative 2, you'd want to be going from the negative side. But generally when we see integrals, generally the bounds are in order, like I want to say chronologically. That's not the right word, but you get what I mean. Yeah, then you can flip the bounds and make it negative. All right, let's go ahead and integrate. So my limit's going to hang around. All right, help me integrate. What's my new power? Perfect. So negative 1/2 here. All right. Let's before I even plug in my bounds, let's rewrite this antiderivative that I have. Because when I plug things in, so this is a little bit of an interesting piece that comes up with improper integrals, or like if you were evaluating just an integral in general, putting things in negative exponents is really helpful for taking the integral, but not necessarily for evaluating. So do y'all mind if I put that x squared back in the denominator before we start trying to evaluate stuff? Like 2x squared here. In my brain, that's a little bit more helpful for when I'm plugging in. So let's start. All right. Plugging in 2 first. So I've got negative 1 over 2 times 2 squared, 2 times 4, negative 1 over 8. Plus 1 over 2a squared. Now, here is an instance, again, kind of like when I plugged in the negative infinity in the e to the 2x question, where I don't really want to plug in 0. This is the whole point, because is plugging in 0 going to cause me some issues here? Definitely. So I'm going to do some scratch work, again, off to the side, so I'm not actually plugging in the 0. Let's kind of reach back, maybe with our AB brains or our math analysis brains or our very beginning of the year brains. Does anyone remember what happens if I take 1 and divide it by a number that's approaching 0? Undefined, let's get more specific. Yeah, you're going to get a version of infinity. So kind of the reverse of what we did here when Rashad said that this traveled towards 0. So I've got kind of the reverse of that process, dividing by something so small we're calling it 0. That's going to pop one of 2 ways, either towards positive or negative infinity. And that's when this plus or minus can make a difference. Here, it's not going to make a difference as much because I'm doing 1 over 2 times some very, very small number, but that very, very small positive number is going to be squared. So even if this were 0 minus for this question, I would still be traveling towards positive infinity. Now, if this had been like cubed on the bottom, that sign change would make a difference. That being said, this guy's going towards positive infinity. If I subtract an 1/8, don't really care. This whole thing is going towards positive infinity. What could you tell me then about my original integral? It diverges. The integral is divergent. So negative infinity, we also would say divergent. That's totally fine.
So I meant to the number that you plug in for the dude.
So for this question, since that guy is squared, we still would have gone to positive infinity. But if that had been like cubed and it had been a negative, we would have gone to negative infinity. All right, so let's talk about this guy here. So do you guys notice that these two questions look almost exactly the same?
What do you do?
Yeah. What's up?
Okay, so you know, like, towards, like, the end of the mountains when you're plugging in,
Yeah.
how do you know whether to add or subtract? Is it
So normally I would subtract this plus is coming from the minus and the negative in the integral. So it's coming from plugging in my bounds. Normally will be subtract unless you're comboing some signs. All right, so one thing I want you to notice, this last one is probably the hardest of all the questions to realize we have an integral. Let me graph it for you, but then we're going to talk about what we really need to check for. Hello. All right, 1 over x cubed, and my bounds are -1 up to 2. Oh, I need to do. Hold on. It's not graphing like I want it to. Nope. All right, I'm just going to turn off the shading for a second. So what I want you to imagine is we're looking at the area between this purple curve and the x-axis. So do you guys agree with me that this, based on the graph, is an improper integral? We have a vertical asymptote happening between our bounds. Yes? All right. The problem is, if I'm looking at this on my paper, that's not super apparent. It looks like a normal integral. And if I went, so this kind of goes back to Victoria's question of like, couldn't I just do all of the work without kind of worrying about the bounds? If I tried to do this and just tried to be like, oh, I'm going to integrate x to the -3 from -1 to 2. I'm going to do, okay, x to the -2, -1/2, -1 up to 2. I'm going to plug in -1/8 plus 1/2. I'm going to get a number. I'm going to tell you this integral diverges. So we really need to be careful because you can't just do normal integral stuff when you have an improper integral. But that means we need to be skeptical now of every integral we see that has bounds. So what you're going to need to do, specifically with the ones that have fractions, is check this denominator. If there is a place where this denominator is going to be equal to 0, which there is, x equals 0 is one of those places, I need to split this integral up into 2 pieces because it's happening between the bounds. Just like with the infinities guy, can't do 2 limits at once. And here I would need 2 limits because I need to approach 0 from both sides. I need to break this integral into 2 pieces, and I have to know to do that because I have to check my denominator. So kind of like the one on the first page, let's do this. We're going to go from -1 to 0. I'm going to do x to the -3 already. And 0 to 2, x to the -3 dx. Notice this time, while the 0 from the first set of questions from the infinity question, that was a choice that we could make anywhere between -infinity and infinity. This 0 is not a choice. This 0 is happening because that's the value that makes this an improper integral. So that's the value I was checking for. I have to break this here. Not necessarily. So can anyone think of a function I could put in here where I would not break at 0? 1 over x minus 2. I would break, well, I actually wouldn't have to break this one. I could just limit out the 2 at the top. Can anyone think of a value that I would have to break it into 2 pieces? X minus 1. I would have to break that guy at x equals 1. So -1 up to 1, 1 to 2. Essentially anywhere your denominator is going to be 0. Because that's moving the vertical asymptote. So graph again. Let's say I took this guy and did this. Notice that vertical asymptote kind of shifts over. Ooh, you guys ask the best what if questions. I love it. All right. So this question I would treat as kind of two different questions. You can kind of do each one separately. So I'm going to quickly roll through this one. If you don't even want to write this down, you might not have to. Here we would be taking b to 0. Notice that the pattern that Kat was talking about is it always b is plus or b is minus and a is plus. This one will hold that way. We're going to be wanting to go 0 minus because we're coming underneath of 0 up towards 0. So from numbers that are negative less than 0. I could already integrate if I wanted to. So I've got x to the negative 2. We just did this integral and we'd be going from negative 1 now up to b. I'm actually just going to kind of follow through the rest of this question. Here we're going to have negative 1 over 2b squared, taking that x squared back down to the denominator, and then plus negative 1, or excuse me, minus negative 1, so plus, let's write minus negative 1, minus negative 1 over 2 times negative 1 squared, or 2. All right, doing kind of my same scratch work as before. This, I'd have my negative 1 over my 2 times now a very small negative number squared. Kind of going back to some of your questions, Rashad, because of this squared, that plus or minus doesn't make any difference. So this guy, the bottom is going to be going towards 0. The top, though, is going to push this guy to negative infinity at the front. That second number, it's very small, so it's not going to matter. You have infinity dollars in debt, and you grab 50 cents off the ground, you're not super happy. Because of this guy right here. So let's talk about the rest of this problem, because this is a little bit interesting. We actually did the second part of this problem. That was the problem we did here. So this infinity is actually on this side. You may be tempted to say a different answer than the answer that's actually there. What are you tempted to say if you see it negative infinity plus infinity? Is anyone tempted to say 0? That would be great if infinities worked like that. But infinities come in different sizes. They're not things that kind of cancel like normal numbers will. So moral of the story, if either piece of this is infinity, we automatically get a divergent integral. Let me write diverges instead of divergent. So this one is a beneficial question to do kind of both sides as separate problems because we can't actually add these together. So this is kind of a situation where I wouldn't necessarily set this equal to anything as the answer. Kind of like, remember when we did one-sided limits, it's very connected. And we could say like it went to positive infinity if both sides went there, negative infinity if both sides went there. But if like one side went one way, one went the other way, all we could say was does not exist. It's kind of like this situation. I can't really say that integral equals positive infinity equals negative infinity. All that integral does is it diverges. Yep. So honestly, what I would do if I were doing this question, I would probably end after doing just this side. If I got that side all the way done and I saw a version of infinity, I already know it diverges. I don't even have to check the second half.
So, if you guys do like on the if we use a different number, you have to show our work for that time.
Explain to me if it was a different number.
So, like, if it wasn't going like, if there was like, because we did zero.
Yeah. So if I had been going even like up to, let's say we're going up to 7, I would still, if I evaluated this first half and I got a version of infinity, I can be done because I know that at least part of this guy diverges. Cool. Again, great what if questions. Also, just talking about prevalence of questions, you're probably not going to see too many where you have to break in the middle. But again, we just have to have now a healthy amount of skepticism towards any integral with bounds. Really, you're checking denominators. Is there any place where we're going to have equals 0? Or you have the nice option, even though some of these integrals were harder, looking at infinity in one of our bounds. Cool. Cool. All right, I am done talking to you for today, unless you choose to talk to me. It is currently 2:11. We get out at 2:28. We're not doing a notes check today. I just didn't really like the notes check questions that I had, and I think you have 3 on your problem set that you can try. A lot of my second block was having problems with the B one, so if you want to try that one under the supervision of someone who's here to help, you certainly can do that. Miss Jillian, what's up? Yeah. Oh, actually, let me show you. Yeah, actually, can I make a couple more comments because Jillian's question is really good? So on the back page here, you're going to notice I have combining these with other things. These are aggressive, to be quite honest, and would not be probably anything I would ask you because it's just so much happening at once. So like partial fractions with an improper integral, that's just straight aggressive. And thinking back of all the problems that I've seen on the AP test, I've never seen them combine them like that. Is it good practice? Absolutely. Is it something that you could probably do? Yeah, it's just probably too long for the test. So I will also come around while you guys are working. I have a present. It's not one you want. I have a test review. So some comments about this unit, something you're probably noticing, more so than other units, I think, is that practice makes these feel a lot better. The more problems you do, the better you're going to feel. I know for me specifically, when I went through BC Calc, I was doing a lot of problems in this unit just because the repetition makes a lot of the choices easier. So I have a test review here, and just to go back to the kind of the directions part, I actually pulled, this is my old test. I committed to rewriting my whole test this year. So these are test questions I've given in the past. This is the directions you're going to see for all of the integrals with bounds questions. It's going to say integrate. Cool. I want to get an answer. And then it's going to say state whether the integral converges or diverges. So those are the, wow, those words did not come out right. Those are going to be the directions that you're going to see on the test if I want you to say converges or diverges. The multiple choice may just have like a part D that says the integral diverges after they give you 3 options of numbers. All right, anything else? All right, now that I've stolen more of your time, you got about 14 minutes. Call me over if you need anything. 4.3.
Thank you.
Oh, bye.
Bye.
Okay, fellas. It's already over. So, is this where you just want?
I have it printed. I can pass it out now. How does Captain's average work in what?
Grades.
The hours later, we're gonna have a meeting for you. Oh, let's have that one bathroom. 70 years? In your classes? So if you qualify for outreach, you are essentially like done with school once outreach starts. You can volunteer in the community instead of coming to school after the second week.
Who decides what like the project?
From my recollection, and again, you're gonna have a presentation from the ladies, I think it's next week. They are going to, there's essentially like an approval process. So you can pick your project, they will either approve it or not approve it. And then
You can feel like your friends somewhere.
you can. Usually it's like groups up to 5, I think.
Oh, what are you talking about that? It's at the end of the year. You can sign up for it. Oh, that's right.
They're gonna give you all the forms this week.
Okay. Already.
Yeah, because there's a whole lot of forms to have.
So, check out me and you, and then we choose all 3 other people.
Wait, you wanna?
May 17th,
Do you all have the same problem set? I was thinking about it yesterday.
Check in with this one.
But it's not gonna be like a
Oh, so you have one actually.
Then we can like little nigga and
Then I'll go back to the.
I kind of want to play this. Oh, God. I'm so busy.
Dark Souls.
Because I think I had 20 hours in one day playing Dark Souls.
Well, I was trying to take,
We need 3 of them?
I took 3 out. I was trying to buy.
No, not for hours. I'm just saying. We need it. Wait. No. You just go here. Is it like a project and like all group would sign up? I guess. Or you go. I don't know. It's like a minimum. Not minimum.
You're not obligated to go on.
I don't know. That's how like people post on Instagram. They want to I don't need it. We need to start. We don't need 3 other people. In our group? Okay. Is there grade amongst them?
Yeah, I've always. Most of my friends are failures.
Talking about us? He's talking about us.
I don't know.
Yeah, skip through the
Is that a 7th edition or black? Black would be with
April 8th or something. And an album starts in a month.
I'm sorry, I didn't hear what you said about this.
So this is just test review. I actually did one.
How do you factor in the factors?
So.
Yeah, it's funny. Okay, I'll try to find my login.
I don't know my login.
No, this is an optional.
I have
Yeah.
I'm in the outline, not like a I don't know if they remember me 5 years ago.
I like your backend though.
I know.
I need some answer keys. Oh, I guess I can stop this recording now. Now that Nate's gone.
So, what if instead of like -1, what if this was like 3?
Good question. So you would probably be in kind of like this situation where both of your bounds are causing a problem. So you'd have to break it somewhere and then kind of limit out each one. That would be a great bonus question.
And then what if you went beyond that and it was like infinity and then there's one in the middle? And then
Yeah. So